Hello everyone, we're going to understand derivatives in calculus in this video. So let's start with the usual friend y equals x squared. To make everything simple, in this video this is the only function we're going to work with. And if you watch my other video on calculating derivatives, we all know that the derivative of y or y prime for our function is 2x. But what does 2x really mean? That's the question we're going to answer in this video. First, let's bring up the graph for the function y equals x squared, which looks like this. Now you should first note that our derivative 2x obviously depends on specific values of x. In other words, if you plug in different x values into the equation 2 times x, you're going to get different y primes. So for example, for x equals 1, the derivative is 2. For x equals 2, the derivative is 4. And when x equals negative 1.5, the derivative equals negative 3. Remember that y prime is not the y values of this graph. Y primes are derivatives, and I'm just putting them on the graph here to emphasize that derivatives are different depending on where you are on the graph. Now in this video, to keep everything simple, we're only going to focus on the point where x equals 1. That's right over here where y equals 1 at x equals 1. And of course, we know that at x equals 1, the derivative or y prime is 2. So then the main question for us in this video is, what does it really mean when we say that the derivative equals 2 or y prime equals 2 at x equals 1 for our function y equals x squared? Well, formally, the derivative represents the instantaneous rate of change of y at different values of x. So that's the formal definition. And in my own words, the derivative represents how fast y is increasing or decreasing at different values of x when the change in x is 0. My own definition is absolutely correct, but in your class, you should probably stick to the formal definition because maybe your instructor is not going to like my own definition. So with all of these definitions, what this means is that at x equals 1, the number 2 somehow represents the instantaneous rate of change of y, or the number 2 somehow represents how fast y is increasing or decreasing. The problem is, we still don't know how exactly we should understand or interpret the derivative 2. We know it's somehow related to how fast y is changing at x equals 1, but we cannot pin down the exact interpretation, at least not yet. In order to understand derivatives precisely, we need to calculate some ratios. So let's go do that. First, we need to consider some change in x. So this notation here, which we call delta x in calculus, is just a notation representing change in x. To start, we can think about increase in x by 1 unit. That means that change in x coordinate is going to be from 1 to 2. So x is currently at 1, but it's going to increase by 1 unit and move to 2. Now we want to figure out what change in y is for our function y equals x squared. Well, as you can see from the graph, y increases from 1 to 4, which means that the change in y is going to be positive 3, right? Or increase in y is 3. Now we arrive at the most important step, which is to calculate the ratio change in y divided by change in x. That's going to be 3 divided by 1, so the ratio equals 3. This ratio is telling us that for our function, if x increases from 1 to 2, y increases 3 times as fast as x increases. Note that this relates to the definition of derivative because the ratio is telling us something about the rate of change of y or how fast y is increasing or decreasing. But keep in mind that this is not our derivative. 3 is not the derivative, so we have some more work to do. But I'm just saying that thinking about the ratio, change in y divided by change in x, points us in the right direction to understand derivatives. So let's come back to our table to do more calculations. And now we're going to see what happens when we consider 0.5 increase in x. What that means is x increases from 1 to 1.5. So on the graph, we're going to have this change from red to green. Change in y is going to be 1.25. And finally, the ratio is 1.25 divided by 0.5, which is 2.5. The ratio is telling us that for our function, if x increases from 1 to 1.5, y increases 2.5 times as fast as x increases. Alright, now we're going to consider a very small increase in x, a 0.01 increase. And I'm not going to use the graph anymore because we won't be able to see the small change anyways. Now, if we do all the calculations, then we get all these numbers, okay? So you can check for yourself. And again, focusing on the ratio, change in y divided by change in x, the ratio is telling us that for our function y equals x squared, if x increases from 1 to 1.01, y increases 2.01 times as fast as x increases. Okay, now I'm showing all the same calculations, but considering a 0.0001 increase in x. Then as you can see at the bottom, the ratio comes out to be 2.0001, which is saying that if x increases from 1 to 1.0001, y increases 2.0001 times as fast as x increases. Alright, finally, we get to the last one where we're going to consider a 0 increase in x. So x remains at 1. And if x doesn't change at all, y also shouldn't change. So that's why the change in y is 0. The big question is, can we still calculate the ratio here? Do we have an answer for 0 divided by 0? Well, the answer to that question is that the ratio when change in x is 0 can actually be solved using techniques involving limit. We'll go over the limit in one of the next videos. For now, trust me when I say that the ratio equals 2 if x equals 1 and change in x equals 0 for our function y equals x squared. So with your trust, I'm going to write down 2 here at the bottom for our ratio. But note that you can still arrive at 2 without even using fancy math techniques. And that's because it's clear that as increase in x becomes smaller and smaller and gets closer to 0, the ratio gets closer to 2. You can try smaller increases in x and calculate the ratio yourself, but no matter how small, you will never get the ratio to be below 2. So again, the ratio becomes 2 when change in x or increase in x is 0. And this 2 over here, that is our derivative for our function when x equals 1. It matches the y prime that we already computed. So then the question is, given our function, how should we interpret the number 2? Well, we can interpret it in the same way we interpreted the other ratios, which is to say that for our function, if x increases from 1 to 1, so if x actually doesn't change at all, y increases 2 times as fast as x increases. Formally, the interpretation you're going to find in textbook is going to be something like, at x equals 1, at that instant when x does not change, the instantaneous rate of change of y is 2. So I hope it's clear by now that the formal interpretation contains the word instantaneous because the derivative is all about situations where x does not change at all. If you don't like this formal interpretation, you can always go back to the interpretation that we've been working with, which is to say something like, at x equals 1, at that instant when x does not change, y increases 2 times as fast as x increases. So this interpretation is absolutely correct, but some picky mathematician may say that it only explains half the story for derivatives. In other words, you can also interpret the 2 here by saying that at x equals 1, at that instant when x does not change, y decreases 2 times as fast as x decreases. How did I get this interpretation at the very bottom? Well, go back to this table that we've been working with, but now consider negative changes in x or decreases in x. If you do all the calculations, then you'll end up with the interpretation at the very bottom. So to be clear, either one of these 2 interpretations are correct, and both of them together provide a complete picture of the derivative 2 when x equals 1 for our function y equals x squared. But you should note that it's more common for people to think about the first interpretation where we consider increases in x. So just keep that in mind. Finally, if you're taking an exam, for example, writing both of these 2 down is going to take too much time. And so I recommend sticking to the formal interpretation for exams. Just double check with your instructor, that's the best way, right? Find out what your instructor wants for your assignments or exams. So I have now given you a couple of different interpretations which are all absolutely correct. But now at this point, some of you may be wondering, how do we think about changes in y when x is not changing at all? It's a bit confusing, right? Like I said, the math actually works out, but the intuition can be a bit tricky. This is why, or this is one of the reasons why many students who already completed Calculus 1 and 2 will interpret the derivative 2 here by saying something like, At x equals 1, y increases by 2 when x increases by 1. This interpretation is absolutely incorrect. When x increases by 1, y increases by 3, not 2. Some of you may be saying that it's still good for approximations, but if you have a different function, for example, y equals x raised to the 5th power, you're going to be way off if you say that at x equals 1, y increases by 5 if x increases by 1. If you come into a master's program in any science like engineering or economics and say something like this, trust me when I say that no one is going to take you seriously. So, one way to answer this question, how do we think about changes in y when x is not changing at all? One way to get rid of this confusion is actually to use really good approximations. Instead of 0, think about a really small increase in x, like this. This is a really small increase in x, right? Almost close to 0. Then if you do all the calculations that we've been doing so far, you're going to end up with these numbers. So as you can see, 2, our derivative for our function when x equals 1, is very close to the ratio. In other words, 2 is a very good approximation to the ratio. Or we can also say that 2 is a very good approximation to how fast y increases relative to increase in x. The point I'm trying to make here is that when you're thinking about a change in x that is very close to 0, although it's not mathematically correct, you can trick yourself for a moment and say that increase in y is 2 times as fast as increase in x in our example. This would be one way to understand the derivative 2 here when x equals 1 for our function y equals x squared. But please remember that derivatives are about rate of change of y when change in x is actually 0.